Alright guys, so here's another interesting exercise that I think you will benefit from. You need to determine the state of stress at point B. Now, as you can see, you have the section where we're trying to get the stress of, it's section AA. Alright, so as if we're taking a section in here. Okay, and we are asked to find the state of stress at this point, at point B. Okay, now we're given the coordinate system, which is x, y, z, and you have a force applied at a 60-degree angle with the horizontal force of 50 pounds. So I'll give you the opportunity to solve this problem on your own. If not, if you didn't know the answer, you will have the right to check out the solution. So step one, as we know, in step one we need to specify a coordinate system. All right, specify a coordinate system. So you should have memorized these steps by now. So the coordinate system is already given for us to be y in the upward direction, z in this direction, and x in that direction. So if you look in here, you can find that the coordinate system is given for you. Now, what's step two? Step two is to draw the cross-section and calculate the cross-sectional properties. So step two, draw the cross-section and calculate its properties. All right. So if you want to draw the cross-section is given for us. It's a hollow cross-section. So we're gonna have a circle in here and another one. It's gonna be a larger circle in here, all right? And you're given that the radius of the inner circle is 0.75 inches and the radius of the larger circle is 1 inch. Okay, so I'm gonna put Rn is 0.75 inches and R out is equal to 1 inch. Right, and we have so if you move the coordinate system, if you want to show the coordinate system, which is a necessity, every time we need to draw the cross section, we need to show the coordinate system. So the y-axis is gonna be like this, so directed upwards, right? Because in here this is the y-axis, so I'm gonna draw a vertical positive y-axis, and the positive z is gonna be directed to the right. Right, so it's going to be directed this way. So this is going to be your z axis. All right. So this is step two. We need to find the cross-sectional properties. So let's start by finding the area. And first, let's locate points B and A. So let's locate point B. This is going to be point B, and this is going to be point A. Right. The one not at the top, so the one that is on the inner circle. As you can see in here, this is point A. If you look at the 3D figure, this is point A. Not at the top, it's at the inner circle, right? While point B is at the outer circle. However, we're not asked to find out the stresses at A. We're only asked to find the stresses at point B. So let's start by the area. This is a hollow cross section. So the area is going to be pi r out squared. So pi times 1 squared minus pi r2 squared, which is 0.75 squared. So sorry, this is squared. Okay, so it's gonna be pi into 1 minus 0.75 squared, which is going to be equal to 1.374 inch squared. You're dealing with inches in here. All right. Now Iz is gonna be equal to Iy is gonna be equal to pi over 4 multiplied by 1 to the 4 minus pi over 4 multiplied by 0.75 to the power 4, and this is going to be equal to 0.537 inch to the power 4, and j is going to be equal to 2 times I, so 0.537 times 2, 1.074 inch to the power 4. So these are the cross-sectional properties. Now we want to represent, so step 3 in here, represent all the forces all right, on the cross section. Represent all the forces on the cross section. All right, so how many forces do you have? Now here's the trick. Here's the trick. Whenever you have an inclined force, find its projections, vertical projection and horizontal projection. Done. Whenever you have an inclined force, find its projections on the coordinate system and then work. So this is the trick. Whenever you have an inclined force, start by finding its projections on the coordinate system. Okay, and in this case we have an inclined force with an angle 60 degrees. If you want to find the horizontal projection of it, so it's gonna be like this, and this is going to be 50 cosine of 60. Okay, I'm gonna call this F1. So F1 in here is gonna be 50 cosine 60, and it's gonna be equal to 25 pounds. And if you find the vertical projection of this thing in here, it's gonna be 50 sine 60, because we're getting away from the angle. So let's call this F2. So 50 sine 60. Whenever you go away from the angle, it's sine. Whenever you approach the angle, it's cosine. So it is 43.3 pounds. Right? So as if I removed the 50 pounds inclined and I replaced it with the vertical projection and the horizontal projection. Now I can work. I can continue working out the problem by moving these forces into the cross section. Alright, so always start by finding projection, then move the forces, or then represent the forces, then represent the forces on the cross section. Alright, how do we do that? Consider F1 which is equal to 25 pounds. We look at the figure. It acts in the negative Z direction. It acts in the negative Z direction because this is the Z direction here. It acts opposite, parallel and opposite to the Z direction. So that's in the negative Z direction. So I'm going to write in here that F1, which is equal to 50 cosine 60, which is equal to 25 pounds, acts in the negative Z direction. So we go to the figure in here and we represent the force F1 like this. F1 is equal to 25 pounds in the negative Z direction. Right? Now what about F2? F2, it acts in the negative Y direction because it's parallel to Y and opposite to Y. So F2, which is equal to 50 sine 60, 43.3 pounds, acts in the negative Y direction. Acts in the negative Y direction. So how are we going to represent it on the cross section? It's going to be in the negative Y direction. So this is F2 equal to 43.3 pounds. Okay, 43.3 pounds. Perfect. So this is it for step 3. We represented all the forces. These are the only forces, F1 and F2, the projections of the 50-pound force acting at 60 degrees with the horizontal. So now after we represent the forces, we need to continue with step 4, and it is to calculate. So step 4 is calculate the moments caused by each force and represent them on the cross section. Alright, so calculate the moments caused by each force and represent them on the cross section. So let's start by the effect of F1. Effect of F1, which is equal to 25 pounds. Does F1 create any moment about the x-axis? So F1, which is this in here, is not parallel to the x-axis. However, it passes through the x-axis. If you continue the F1 vector, you're gonna hit the x-axis in here at this point. Alright, so this means since F1 passes through the x-axis, this means that it doesn't create any moment about the x-axis. So mx due to F1 is 0, because F1 vector passes through the x-axis. Now what about My? Does F1 create any moment about the y-axis? F1 is not parallel to the y-axis, otherwise it would be in the vertical direction. It doesn't pass through the y-axis because if you continue the F1 vector, you're not going to hit the y-axis, which is the vertical axis. Therefore, there is a moment created by F1 about the y-axis. And to find out the magnitude of this moment, let's draw the y-axis in here. And draw the force in here, F1 is equal to 25 pounds. The distance that we're going to use is the perpendicular distance between these two. Always, the moment is a force times the perpendicular distance. What is it on the figure? It's going to be equal to 10 inches. F1 multiplied by 10, you get the moment caused by F1 about the y-axis. So in here, you have 10 inches. And so the moment about y is going to be equal to 25 pounds multiplied by 10 inches, which is 250 pounds inches. Now, is the moment about the y-axis a bending moment or is it a torsion? Of course, it's a bending moment, it's not a torsion, because the torsion is a moment about the axis that doesn't appear on the figure, which is the x-axis. So My is a bending moment. Where do you say the compression and the tension regions are? To the right or to the left? Above or below? The tension and compression regions are to the right or to the left of the y-axis. Whenever the moment is about a vertical axis, then the compression is either to the left or to the right of the vertical centroidal axis. Very important. Alright, so My is gonna cause compression to the right or to the left. How do we know? To know where the force causes compression, we follow the rotation of F1 about the y-axis. So notice in here that we have the cross section like this. Alright, this is the cross section like this. It's a hollow cross section, the one that we drew in here. Okay, if you want to see it at 3D, it's going to be like this, as if I'm drawing the cross section in plane AA. So what's going to happen is if we follow the rotation of F1 about the y-axis, you're gonna get something like this, right? So the force is gonna rotate like this, so you're gonna have this rotation about the y-axis. All right, now since we're working with this cross section, all right, where are we entering into the page? So if we follow the rotation of F1, we are entering from the right of the y-axis. We are entering from here, right? This is where F1 is entering, and then it is continuing the rotation. So this place in here is the compression zone, and this means everything to the left of the y-axis is in compression. All right, everything to the left of the y-axis is in compression. Now, so I'm going to show it to you on 3D also. To find the compression zone of the moment caused by F1 about the y-axis, follow the rotation of F1 about the y-axis. You're entering from here, right? Because F1 is going to rotate like this. Okay, so you're going to enter to the left of the y-axis, and therefore you're going to have a compression to the left of the y-axis, right? Compression to the left. So if you want to present it on the figure, you're going to have My compression at the left. So this is My, and it's equal to 250 pounds inch. Alright. Now what about Mz? Does F1 cause any moment about the z-axis? It doesn't, because F1 is parallel to the z-axis. So since F1 is parallel to the z-axis, this means that Mz is equal to 0. Now, let's consider the effect of F2, which is 43.3 pounds. Does F2 cause any moment about the x-axis? F2 is not parallel to the x-axis because this is F2. It's not parallel to the x-axis, nor does it pass through the x-axis. Therefore, yes, it does cause a rotation about the x-axis. So there is a rotation, This is the x-axis, and this is F2 equal to 43.3, and the perpendicular distance between them is this. If you continue the x-axis, this is the perpendicular distance, which is equal to what? It's equal to 12 inches. It's equal to 12 inches. So mx is 43.3 times 12, which is 519.6 pounds inches. We need to find the direction of, we need to represent it on the cross section. Now, the moment about the x-axis, what do you call it? Is it a bending or a torsion? It's a torsion because it's a moment about an axis that doesn't appear on the figure. Okay, so this is a torsion. So the way you're gonna represent it on the cross section is either clockwise or around the circle or anti-clockwise. How do we know that? If you look, we follow the rotation of F2 about the x-axis like this. It's gonna be like this, right? Rotation of F2 about the y-axis is gonna be in the clockwise direction because the cross section is sitting somewhere in here, right? Sitting in here. So as if the torsion is creating this rotation, which is in a clockwise fashion. So we go to the figure in here, and we have a torsion like this, clockwise. Torsion is equal to 519.6 pounds inches. So this is mx due to fz. What about my? Does fz create any my? Does F2 create any my? The force vector F2 is parallel to the y-axis. This means that my is equal to 0. So my in here is equal to 0 because F2 is parallel to the y-axis. What about mz? Does Fy create any mz? Does F2 create any mz? The force vector F2 is not parallel to the z-axis, nor does it pass through the z-axis. Therefore, yes, it creates a moment about the z-axis. Okay, so we go in here. The z-axis is going to be like this, and F2 is going to be like this. This is F2. It is 43.3. The perpendicular distance is this. Right? Which is what? On the figure, it's 10 inches. Okay, the perpendicular distance is this. It's 10 inches. Okay, so distance is 10. So here you have it 10 inches. And then the moment is 43.3 multiplied by 10, which is 433 pounds inches. Now, where do you say the compression zone is and where the tension zone is? Again, we know that the cross section again, we know that the cross section looks something like this in here, right? It's a hollow cross section. And to know where the compression zone is and where the tension zone is due to mz, we follow the rotation of F2 about the z-axis. So it's going to rotate it that way. You're going to enter from the bottom, and then you're going to have this rotation about the z, right? As if you're having this z, and the rotation of F2 is like this. Okay, so the place where you are entering into the page, which is everything below the z-axis, is in compression. Because, so as if this is the z-axis and this is F2, you are entering into the section from the bottom. This means that the bottom is under compression. So we go in here, and you know that the bottom is under compression. This means that the arrow is the moment flash is oriented downwards because the arrow reflects compression zone. So this is going to be mz, and it's going to be 433 pounds inch. Alright, I'm gonna stop here for this part. We're gonna continue our calculations in the next part. So see, it is very crucial that you know the directions and the magnitudes of the moments that are applied at the cross-section of interest. Once you have the cross-section with all the forces and the moments represented on it, then we can proceed by calculating the shear and normal stress at point B. We're gonna do that in the next video. If you have any questions till now, please let me know. We're gonna continue calculations in the next part. I'll see you soon.